All right, 2018 question. I just selected this part out of it because it's talking about radioactivity. Um, but if you want to go back and check the past, the other questions, then you can do that. All right. So I was just saying a while ago that whenever you see a question, right, it's value 1 mark. You know that tell you it's supposed to take you 1 minute to answer it. Now when you look on this first question, it's value 1 mark. It's supposed to take you 1 minute. So the less time you spend on the first question, it's the more time you're gonna have to can spend on the other one. So that's how you conserve marks. So clearly it says right the exponential decay equation for radioactive material. What do you think the equation is, guys? Tell me the equation.
That would be, wait, the exponential radioactive materials. Isn't that the same one that we just did?
No, you tell
The
me.
n equals n naught,
You,
exponent.
go on. Go ahead. Go ahead, please. Where's Campbell? Isabel, go ahead.
Sorry, sir.
Okay, go ahead, Campbell. Then. Ready now?
Oh, okay. Sorry. So there's n naught, the exponent, right? Exponents lambda negative lambda t, and the n would be the number of nuclei remaining, right? The lambda is the decay constant as time passes. And n naught is the initial number of nuclei. So would we, okay, just the equation, right? We don't have to like.
Oh well, I think we did the wrong thing here. I was doing another something here. It says identify the decay constant in the equation in that above. So clearly the decay constant, would be lambda. So that's a very simple question. So you can just say that the decay
Yes, sir.
constant is lambda. And you see, they ask about the units now. They ask about the units, So the units here, we say now it's going to be per second because the K constant is technically um, n upon time, I think. That's what it is, right? Because it's basically the number of, I don't even know. There's a definition for it. The K constant is the number of nuclei per unit time. So that's how we get this. The number of nuclei doesn't have any unit, but the time has a unit, so that's how we say it's per second, right? So that's that. So let's review this part from to just understand what the decay constant, how you define it, so to speak. But I believe it's basically the number of nuclei per unit time, and you basically get the 2 marks. That's what I mean. So you see even more minutes because it shouldn't take you that long. Then now it goes to the next question now, and it says go ahead and look at this. It's talking about a count rate. Let me just say something here that we can do experiments to basically carry out some type of radioactive decay, so to speak. So the data that you're looking on here is just showing you, uh, what is essentially happening to the radioactive substance. So what you're seeing here is that when the time is at 0 minutes, right, it has a very high count rate, meaning that the count rate meter um, or the Geiger Muller tube is detecting a lot of radioactive substance. Now, as time progresses, we're seeing that less substances is being detected by the actual experiment or whatsoever device is collecting the data, right? So the count rate is just simply counting the number of radioactive substance that it is detecting. So remember now the radioactive. So whenever a radioactive substance goes through the process of decay, it gives off alpha particles, it gives off beta, gamma, all of those kind of things. So what the device is doing is it is either picking up the substance that is being released, the radioactive isotope. It's either picking up that, right, to show you that that is being given off from the substance mainly. So that is technically what is happening. right? In the process of disintegrating and all that, all the way up to 180 minutes. At that time, we can record four count rates, right? So we know that it's going through a decay process. So we expect a graph looking like this. So they say go on the graph paper, and it tells you, it says plot a graph of count rate versus elapsed time. It says draw your best curve through the points. Okay? Then another part of the question now would say draw the tangent to the curve at the point where t is equal to 0 and produce the tangent to intersect the t-axis. It then goes to say read off the value of t at the point of intersect. So it's nothing hard that we're doing so far. It's just following procedures. So this is what my graph would have looked like when I went ahead and prepped it up for you guys. This is the best that I could have done at the present moment. So I would have plotted the graph, use my scale. So this over here so is what again? I don't remember, but this is count rate, right? And I don't even know the units, but you can go back to your table and find out the units, all that kind of stuff. This is obviously time, and it is in meters, minutes rather. So when I draw the curve, this is what I got. Mine look a little bit crooked, but yours supposed to be a smooth curve. Smooth curve, not looking like mine jiggy jaggy, because I couldn't do any better. But you're supposed to have a smooth curve, right? Going through the point. So you just need to position the pen on the paper, and you just go right down and curve it around like that. You must pass through the point mainly, guys. So please don't have the point being way over this and the curve the way over this. Have to run along it. So they said to us we should draw a tangent that starts from 0, or basically the tangent is coming from 0, right? But then that line must pass through the time axis, the t-axis. So this is your t-axis. Technically your x-axis, your t-axis. Then they tell us to read off the value. So all you just need to do is to go on your graph and read the value right here, so where it cuts the t-axis.
Yes.
Okay. Yeah, man. So I hope that you guys will practice this question, the 2018 paper question, just for your own benefit, just the same way, right? Get yourself into the habit of plotting graphs and all that. But the graph is very easy, not a very hard thing to do. So it's, wherever the line intersects here. So the thing is, you see, when it comes down to a physics exam, it's not always about, applying knowledge or definitions and all those things. It is some simple stuff sometimes, but those simple stuff might look complicated to you. Because back in the days, I could say that these things were complicated, but I guess as you grow older, it doesn't look so complicated again, right?
Sir.
Yes, Campbell.
Can you please as you were saying, it seems complicated. Yes. The way the question is structured, I didn't understand a thing. So could you please go back to that and show me how you got that line, the tangent?
Okay, let me show you the question again. So the question here, so you understand to plot the graph, right? That shouldn't be anything hard to do. Cool? You follow me?
Yes, sir.
Then the question goes to say, draw a tangent to the curve, right? At point where t is equal to 0. And it says produce the tangent to intersect the t-axis. Now, when you look back at the graph, so your curve would start at 0 because the fact that, 0 is one of your points. So that's where your graph starts. So when they say draw a tangent now, they mean that you should draw a straight line. A tangent is a straight line that touches the curve one time. And that line will come all the way down. Let me show you what it should look like. So this is what it must look like, right? That is what the curve should look like. When I look at this, I realize that mine was close to it as well. That's what I mean. Because mine was in the 40 final, yeah, basically where it cuts is 40 region here. So technically that's what you're supposed to have. So this is where 0 is. This is where the graph starts. So that is just a tangent from that point come all the way down here. So straight line. Then you would read off the value from the graph where it intersects. So once you find that value, you would just document it. Let me see what value that they produce here. Right, so that value so we're going to basically use the value I think based on what they said here, they said that, you know, whatever value we use, we just use that value. So when I go back to my graph, which is this one here, let me see now. So this is going to be about 48 minutes on my graph. So let me go back to my PowerPoint now. So that value for me is 48 meters. So it doesn't matter if your value is way off to some degree, but once it is correct in terms of what it's supposed to be like, then you should produce that value. You should do it as such. Let's see here now. So it says that it can be shown that the half-life, right, is equal to 0.69 this symbol, right? I can't tell you that this is theta, but this is called tau, where tau is the value of t at the point of intersection with the tangent. So tau is equal to the value that we just found, which is 48 minutes for me. So technically they're saying that the half-life is equal to 0.69 of that t value, which is basically tau, right? 48. So it says calculate the half-life using this formula. So when you take a calculator now, right? So 0.69 times 48, I get that the half-life is going to be 33.12 minutes. It has to be in minutes, okay? So that's the half-life. It goes on to say determine the half-life by directly reading off from the graph and suggest a reason for any discrepancy between this value and the calculated value in C. Okay, so it's almost like an experiment, or not an experiment, but that is like what you would do in some experiments, like to talk about why a value is far off from the next value. So what we're going to go back to do now is to essentially find out the half-life. So for us to find out the half-life, we must know the initial amount that we start out with. So let me go back to that. The initial amount was 72 rather. So if we start with 172, what would be the half of that amount? if we start off with 170, 173, 72 rather, right? You guys with me?
Yes, sir.
If I start out with 172, what would be half of that then?
So you break up. Repeat that one more time, please.
Yes, if I start, so my initial amount, so we want to use the graph. So the question is to use the graph to find the half-life. How do we go about finding the half-life using the graph again?
Well, you just have to half it.
So half the initial amount, then what?
Yes, sir. And then you have to well, look at the graph and see what time correlates with it, and that would be the half-life.
Perfect. Campbell, are you with me still? So remember now, n is equal to
Yes, sir. I'm here. It's just crappy internet.
so n is equal to this amount. We start out with this, n naught rather. N naught is this. So a half of n naught would be 172 divided by 2, which gives me 86. So I need to go on the graph and find 86. So 86 over there, boy, yeah, so. Right? So all I do is to go across, and wherever it touches the curve, right? Then I would just read off the corresponding time value, right? And based on this, it is telling me, so this is 20, and this is going to be what? Let me check something here. So this is 20, right? Half of what? Yeah, 20. So technically it's going to be about 33 or so, or 32, 33. It's going to be about 35. Let me just see. 20 divided by 5, right? 5 times 3, 12 plus 30 plus 20 rather. So 32, around 32. So this is about 32 minutes that we are seeing here for the half-life. Remember first we said that the half-life is this, not true? Right? So now, going back to the question. Going back to the question now. They said that we should determine that value. So we say that it is 32 minutes. Right? When we compare it to this, okay, I see now. Okay, yeah. So you realize that the values are not that far off based on the calculation here. Right? So this is 32 and this is 33.16. So yes, they are far off.
Sir?
Yeah, go ahead.
Where did 32 come from? I'm sorry, internet went out.
Yeah, the 32 came from the graph. Right? So based on my reading of the graph here, so I would have identified where the half of the initial amount is. Then I would have found the time value for that. That time value will tell me the half-life technically. All right? Follow me? Are you there?
Sir, all of that was just in vain. It's recording, right? I think I'll just rewatch that part.
It's recording. But I'm saying that you just read the graph as how I showed you how to find the half-life from the graph. That's exactly what we're doing. So when you read the graph, you get this value, 32 minutes. Then no, the question continues.
No,
right?
sir.
Yeah.
Sir, I know you're speaking, but like what I was saying is not that I'm not understanding, is because I cannot hear you clearly at all. So you're repeating, but I'm not actually hearing much from you. It keeps going in and out, and I know it's my internet. So
it doesn't have to be your internet only. It can be my internet too. Follow me?
Okay.
Yeah, it's being recorded. And I'm going to post it instantly, right, as soon as I'm finished here, mainly. Yeah. But no, it goes on to say, suggest a reason for any discrepancy, right, between the values, this value and the calculated value. So you could simply say, you know, due to the fact that the curve might not have been drawn accurately, right? We could say that, um, let me see what they have here, right? So these are some of the possible reasons, ladies and gentlemen, right? So it could be random errors in the count rate, right? You said incoherent, inaccurate, inaccuracy in graphical method, inconsistency in background radiation. It says difficulties in drawing a smooth curve, right? So as it pertains to the inconsistency in the background radiation, what you must understand, ladies and gentlemen, is that there's something what we call background radiation, and I think you guys should look up that as well. It's in the PowerPoint that I would have made available to you guys. Please let me know if you have the PowerPoint. But background radiation is a radiation that is within the environment at all times, right? So as we speak right now, there's background radiation. So within the experiment, the possibility is that there will be background radiation that could interfere with the possibly count rate of the experiment. So you could factor that in as well to say that there's inconsistency in the background radiation. I mean, yeah, so that can affect your results. And I think there is something else that you should be mindful of. Like if you're doing an experiment, and this is probably for Isabel now, if you get an experiment talking about radioactivity, there will be a point where you will have to, if you're trying to find um, the count rate, right, for a particular radioactive substance, there is something, I don't remember it quite well, but there's something where you have to subtract the measured count rate, right, right, the measured count rate from basically the background count rate, count rate. So what you would do is that prior to measuring the count rate of the sample, you would allow the experiment or allow the device, which is possibly a Geiger monotube, to measure the background radiation. So you just have it open, you just have it running in the room for a period of time, and it will pick up some radiation. Then you would conduct the experiment now using the sample and all of that, and then now you're gonna get a value. That value is basically the count rate of the substance plus the background radiation. So to get the corrected count rate, right? Would you just subtracting the measured count rate from the background count rate, technically? So that's something to take note of when you're looking at radioactivity on a whole, right? And if you check textbook, you might see information related to it in there. Okay.
Yes, sir. So, sir, the same thing picks up the corrected the background count rate, right?
So it again.
I said the same device will pick up the background count rate,
Yes.
right?
Yes. Yeah. The same device will pick it up. More than likely, you would be using a Geiger-Müller tube to detect the substance. So that Geiger-Müller tube can pick up the background radiation. All right. and there are certain when you talk about background radiation, it's just a myriad of things that can cause background radiation. I mean, when you think about the sun's ray, right? The sun gives off background radiation. There is radiation being emitted from devices, all of those stuff. Anyways, it says that if the initial sample contains 50 grams of a radioactive substance at the start of the experiment, it says determine the um, quantity remained in after 4 hours, right? So after 4 hours, um, they want us to find out how much of the substance is remained, right? Let me see here. I mean, there are several ways we could do this. Mainly, right? Let's do something here. 4 hours times 60 gonna be 240. We said that the half life was technically 32. Let's just put it as that. Right. Let me try something else here. Plus that and that. Da, da, da. 3.0. Okay. All right. Let's try it this way. Right. So, let me see here. If I know, sorry, I know the half life technically. Um, Based on how they did it, right? I mean, it they show several ways, right? So based on their calculation for the half life, their half life was about this amount, right? About 30 minutes. Now, if I am running the experiment for 4 hours, right? That amount of minutes would be about 240, 240 minutes, right? Because 4 times 60 give me that, right? If I divide um if I divide 240 by the half life based on what they have here, I will get 8 half lives, right? So in 4 hours I have 8 half lives. Then some other crazy stuff happens here, which I I don't quite capture it mainly, right? But the way how I would do this, 'cause I don't like when they do these parts, like these things here kind of be a little bit uh you know tricky somewhat. I don't fully quite get this, you know what I mean? But let me show you what I would do, right? I could find the decay constant, right? Since my half life, right, is equal to 0.693 divided by lambda. I could transpose to make lambda become the subject. So I have 0.6 93, divide that by the time constant that I found, which was what, about 32 point 0.5. I average those values, so let's just work with that. When I work this out, right, 0.693 divided by 32.5, I get a decay constant of 0.02. Now, using this equation that says n is equal to n naught times e to the minus, you know, um, decay constant times t times t, I could now use this equation to find out the value technically. The sample that I started with is 50 grams, e raised to the uh, 0.02, right? The time is going to be 240 minutes. You have to convert from hours to minutes. So let's work out the power section here. So 0.02 times 240, um, n is equal to 50 e to the minus 48. I mean 4.8 rather, 4.8. So let's work out e to the minus 4.8. When it comes down to this e, I have to press shift ln, right? That's what I have to press to get that e. When I did that, I got 8 point. Somebody do it for me, please. Let me see if you get the same value. I think it's 10 to the minus 3. I don't know quite because my calculator is not showing everything. Let me know. Put press ln. Well, press shift ln and then put in the minus 4.8 and tell me what you're getting.
Sir, I just had some connectivity problems. Could you just run through
What did you say?
this quick? I just had some connectivity problems. Could you just repeat what you just like said?
Okay. Campbell, are you there with me? Campbell, you lost in the woods? Okay. All right. So what I was saying a while ago, I think you would have caught some aspect of it mainly. But what I'm doing here, so what I want you to do for me is to put ln, well, shift ln, then you put negative 4.8 in your calculator and tell me the value you're getting. My calculator not working so well. I think I need to invest in one. But shift ln, then you put minus 4.8 and tell me what you're getting. You follow me?
Sir, I don't think I'm getting, yes, sir, but I don't think I'm getting the correct value because I'm getting a really big number, getting 513.2.
Okay, okay. Not sure why that is happening. Right, you always have a weird calculator, you know. But I just wanted to confirm that. Let me just check something here quickly to see if that value that they got is close to what I got. So for the value that they got is point 0.2, right? And I mean, you might not get the same value in all working out because your graph might not be completely related to their graph mainly. There's a thing, if you can remember it, it would be a little bit more beneficial to you, right? But this thing here that says fraction remaining, there's a formula, right, that says half. Let me just show you what I mean with the equation. There's an equation. By the way, what I did here is not incorrect, just so you know. It's just that maybe because the fact that the values that we're using is not completely the right values and all that. But and because we're doing a lot of calculation, but there's a thing here that says half n, well, half or 1 divided by 2 raised to the n. This n tells us the number of half half-life, because we found out a while ago that with this particular substance, right, within 40 hours, not 40, but within 4 hours, it would have 8 half-lives. So 1 divided by 2 raised to the 8, right? Uh, would essentially kind of tell you the remaining number of the substance. But because we're dealing with 50 grams of the substance, right? We now have to, rather than having 1 here, right, you would now have 50 divided by 2 raised to the 8. See what I mean? I have to go review this for myself, like to completely get this whole thing. But this would kind of help us in finding the answer much quicker to some degree, right? But as I said, there are 2 ways you could do it. You could do it this way, but as I said, go through the book and see if you can understand this part. Because it's not all the concepts I have fully grasped as relates to this part. But this is the equation you could have also used to find out the remaining substance, right? So yeah, that's it as it relates to this part too. Um, Practical more questions related to these questions, the radioactivity, of course.